P square over 2m sum. This is the total energy which is given to you. That is the constraint, and under that situation, I have to find what is the number of states available to me. Which means that if I'm talking free particles, so if it is free particles that I'm looking at, then V is equal to 0, and my constraint is P squared over 2m plus P n squared over 2m is equal to E. The integrals over R1, R2, Rn are independently doable because there is no V over here. The particles don't, that this constraint is about the potential energy, plays no role. So it is, if I'm confined in a volume V, so particles confined in a volume V, then each of these R1, R2 to Rn are free to go over the entire volume independent of each particle, independent of any other particle. No interaction, so no constraint. This particle can be here, that can be there, this can be here, and so on. And then they can, I mean, this being here is no way affected by this being here, and so on. So all these R1, R2, Rn are independent of each other, and therefore, if I'm talking about free particles, then this integral over here, each B3R gives me, so each B3R gives me a volume, total volume V, and therefore I have V to the power n coming from over here, and there is H to the power 3n, and then there is D3P1 to D3Pn subject to the constraint that so this is subject to the constraint that P1 squared over 2m up to Pn, the total energy is given. So if this is the constraint, then the particles can lie only on the surface. So this equal to constant is, this equation is that of a sphere. So P1 squared up to Pn squared is equal to 2me. So this is a sphere in the P space. A sphere, the P space is 3n dimensional because I have Px, Py, Pz associated with each 1, 2, 3 to n. So this is, there are 3n square terms over here.
For each one, x, y, z.
X, Y, Z. So, if it's just one particle with the energy E, that's a sphere in a three-dimensional space. N particles in 3 dimension, it is a sphere in a 3n dimensional space. So, and the particles live on the surface, and therefore the task is to find
particles leave from the surface of that
sphere, three-dimensional sphere.
three-dimensional momentum sphere.
Yeah,
Is there?
it's free particles. Therefore, they have to. If the energy, total energy is fixed, then P1, P2 to Pn, these are the vector p's for each particle. They satisfy this relation, and each P1 square is Px1 square plus Py1 square plus Pz1 square. So actually, if written out in full, this is Px1 square plus Py1 square plus Pz1 square plus P2x square plus P2y square plus P2z square, and therefore there are 3n square terms over here. So therefore, it is a sphere in a 3n-dimensional space, and my task is to find the surface area of a sphere in 3n-dimensional space. So we'll do it. I mean, since it can be, if it was two-dimensional particles, then it could be a 12-dimensional space, and then if this included a harmonic potential, then you should. So in general, I will address the question that what is the surface area of a three-dimensional sphere. So thereafter, you can just, this answer for D, put whatever D is for the problem at hand, and you get the answer. So my task is to get volume and surface area of a three-dimensional sphere. So I need to.
Means the particles are moving inside that volume D space. The particles are moving randomly inside the box. But you are saying the particles are moving freely over the surface.
Because there is a constraint. So if I just think of one particle moving with a fixed energy, free particle, which px squared py squared over 2m plus pz squared over 2m is equal to E. So px squared plus py squared plus pz squared is equal to 2me. The particle will have to move in such a manner that energy is conserved. Therefore, its x, y, and z momenta would have to this, and therefore, in the px, py, pz space, it lives on the surface of the sphere, which is given by this.
Okay, this is going to be a momentum sphere. The momentum space is the sphere which is in the momentum space, px squared, py squared, not in that R space.
R space the free particle.
R space for free particles.
Sorry. Every particle is characterized by x, y, z, px, py, pz. So the dynamics of every particle in a 3D space is specified by x, y, z, px, py, pz. So in general, for a single particle, I would have px squared over 2m plus py squared over 2m plus pz squared over 2m plus v of x. V is the potential, not the volume. This is equal to E. Huh? So if it is a free particle, then phi is just 0 and therefore it reduces to this. If this is a particle which is in a harmonic potential, phi is equal to 1 omega squared x squared plus y squared plus z squared, then the constraining equation would have to be that px squared plus 2y py squared over 2m plus pz squared over 2m plus half m omega square x square plus half m omega square y square plus half m omega square z square is equal to E, right? So then it would have to look like this. And where is the, what does this constant look like in that case? Well, what I will do is instead of this x, y, z, I would scale it. All right. In general, what would it be? This is an ellipsoid in a 6-dimensional space. Right? I mean, so this is a ellipsoid in a 6-dimensional space. I can carry out a transformation so that m omega square x square is equal to some capital X square over m. So I do a transformation x equal to capital X by m omega, and if I do that, then this becomes x square over 2m plus capital Y square over 2m plus capital Z square over 2m, and in terms of px, py, pz and capital X, capital Y, capital Z, it is again constrained to lie on the surface of a sphere, but this sphere is in a 6-dimensional space.
It had been in 3-dimensional, it is in 6-dimensional. It was 3-dimensional for free particles.
Yeah. I can have in a arbitrary vector V. So a vector V can have, I mean, you are used to seeing all these things in 3 dimension, but does not matter. A vector V is a quantity which has components x1, x2, can be up to xn, and that defines a n-dimensional vector. The vector V, it can be a single line on which the vector lives, or it can be a surface in which, then it can be a volume in which, but then I can, the rest, then it becomes abstract. What I learn from here, I can continue that to several arbitrary number of dimensions, and the vector can be a vector with n components x1, x2 to xn. And there the magnitude of the vector has a direction in that n-dimensional space. It also has a magnitude in that n-dimensional space, and that magnitude is given by the components v1 squared plus v2 squared up to vn squared, and that is equal to v squared. That defines the magnitude. It may not happen that this is going to be this, as you will see later, may not be the way you want to define the magnitude, or you have probably done more special relativity than most people do, and therefore over there the quantity was c squared t squared minus x squared minus y squared minus z squared. The space was four-dimensional x, y, z, and t, and the thing which was constant was not a sphere but lived on a hyperbola. Huh? So over here, there is no question of time, so there is no question of change in the signature, and therefore all that we are doing is standard particle in a Euclidean space, but instead of one particle, I have n particles. So n particles, if I have to represent them, I need n vectors, n 3D vectors if it's in a three-dimensional space, 2D vectors if it's in a two-dimensional space, and 1D vector if it is in a one-dimensional space. So x1, x2, each one of these, each one for the particle number 1, 2, 3, and each one a vector in the corresponding physical dimensional space. So this can have three components in a three-dimensional space and two components in and so there can be 3n numbers over here. That is what I'm saying. That these are actually, I mean, this is, and we have to specify by position and by momentum. So there is, I mean, in general, there are these. So these are n 3D vectors, n 3D vectors to specify a space and specify a state, and then how do I draw the state? The whole point which we have been talking about in this dynamics, the state is a point in the phase space. So how many dimensions does this phase space have? It has, I mean, 6n dimensions if I have n particles moving in a three-dimensional space. It has 4n dimensions if n particles are constrained to lie on a plane, and 2n dimensions if it is the particles are constrained to lie on a line. So the number of axes that I need to specify the state of the system in general is 6n for particles in a three-dimensional space. So all the while we have been talking about, we have been drawing this XP space, and the state of the dynamical state of the particle was a point over here. But how many pieces of information do you need for that point? If it is a three-dimensional space, then for that point you require, and it's an n-particle system, it requires 6n specifications. I mean, is that clear? I mean, because after this, things are just back, but this picture should be clear that this big phase space has dimensions which are related to the number of particles and then to the actual physical space dimension where they are moving around.
Actually, sir, means we are thinking in terms of the direction that is here, 3D, 4D, that x, y coordinate planes. But the px, py, pz, that is in mathematical surface. That is,
Yeah, absolutely. But the moment one started talking about phase space, it was always x, y, z, px, py, pz. So it was state of the particle was shown as a point in the phase space. But that point has all the information x, y, z, px, py, pz. Yeah. So 6 points required to specify the state of a single particle.
yes.
Yeah. Yeah, I mean, So the whole idea is that I have this, I want to know over what volume, in the volume of phase space in which these particles live. Living is determined by just a point in the phase space and its a trajectory for a single particle. But now it is the system living. System is in particles, and so this space is maybe 3 n-dimensional, maybe 6 n-dimensional, which is the maximum, and so on. But therefore, I need to know what happens in an arbitrary d-dimensional space if I have a d-dimensional sphere, because that's the only figure that I can deal with. Then what is the volume and what is the surface area? So, all right, you know a few things. D equal to 3. The surface area of the sphere is 4 pi r squared, and then the volume is 4/3 pi r cubed. D equal to 2, it is 2 pi r, and for this, and it is pi r squared for this. D equal to 1, it is 2L for this, and it is just, I mean, essentially points. So I have D equal to 1, particle has a given momentum p squared, so given energy, so P can be plus P, so square root of 2mE and minus square root of 2mE. So those are the 2 points in P direction which it can occupy. And what is it in the x direction? So if the x, so this is my P direction, and here is x. In x, it is all the way between plus L and minus L. So so this is or 0 to L, whatever. So if it is L to minus L, then it can go. So what is it? What does the if it is determined by square? There's a line over here, and there is a line over here. So single particle in the XP space. So here is my XP space over here. This is P, this is X. There are two P's available to it. This is P0, let's say, and this is minus P0. And at minus P0, it can go on this line. From this is L, and this is minus L. So it can move from here to here, or if it is at minus, then it can move from here to here. Right? So that's the. So in that's a one-dimensional particle in one dimension, and it is in. I have to picture the state. One particle in x in terms of x and p, and the allowed energies are this is square root of 2mE, and this is minus square root of 2mE. So it can either have be on this line, or it can be on this line, but the whole line is not accessible. It is only between plus L and minus L, and if it has this momentum, again between plus L and minus L, and therefore the trajectory of the particle is limited to this. If it is a single particle in 2 dimensions, life becomes immediately more complicated, because if you are saying that it is in the xy space and you are confined to the region x square plus y square less than equal to r square, then it is Huh? So in the XY space, it is going to look like this. But now that is only for a given momentum, right? So the momentum once again can be is determined by px squared plus py squared is equal to 2m E. So if the energy is given as the particle is constrained to be confined in a cylinder, so that is the or a cylinder meaning this circle x square plus y square. So physical space region is this. So far as momentum is concerned, now it has to be, I mean, you would have to have two more axes. I can't draw the fourth one, but in that axis also it is it is a circle in that axis or in that plane also, and the whole thing is this circle and this circle jointly. I mean, points have to be both within this circle over here and the pxpy circle that is not. So all the phase space region is going to be if it was a single particle, but in a simple harmonic oscillator, one t equal to one, and simple harmonic oscillator, then it would be half m omega squared x squared equal to e, and the particle trajectories would be now on this ellipse, which I can make a circle by doing a little rescaling of the ends. So if I have a capital X here and a small p, this capital X is rescaled to make this a circle, then you have the particle is going to move on this circle, instead of the two lines that we had over here. These two lines correspond to free particles. There are two possible momenta, and then it can go between minus L and plus L. But if it is a single harmonic oscillator, then that's the constraint, and the XP representation is this.
It would be ellipse.
Huh?
Ellipse.
Ellipse, but I mean, I would, instead of using small, if I use the small x, I would have an ellipse. So I use a capital X, which is defined as small x times m. What I said a minute ago. I mean that I want to write this as capital X squared over 2m. So capital X is equal to m times omega small x into m omega. Then it is p squared plus a capital X squared equal to 2m.
Means every time you can make a sphere.
Huh?
Every time you can construct a sphere.
Every time I can construct this. For the simple harmonic oscillator. So how do I know that the area of a two-dimensional circle is pi r square? So normally, I mean, you know, I've done this by taking strips, drawing a circle over here, and you take the circle is x squared plus y squared equal to r squared. You draw strips of this kind, integrate over the strip, so the strip is dx times the length over here, then you integrate according to this and you get the area from this. I'll get the area different. I'll do e to the power minus x squared into e to the power y squared dx dy over this circle. So over this inside this that is xy constraint to be within this circle over here, I'll do the integral e to the power minus x squared e to the power minus y squared dx dy, and instead of, let's say, keeping it within the circle, I don't want I want to do this integral over the entire plane. So I want to do this integral over the entire plane, and my answer is, so this is dx and dy both going from minus infinity to plus infinity, integrals factored. The answer each gives me a square root of pi, so the answer is pi.
And why minus infinity to infinity? What the
Doing it over the entire plane. I'm doing this integral over the entire plane. So root pi for each integral, so square root of pi times square. Huh? And these integrals factor. I mean, here this is equal to minus infinity to plus infinity e to the power minus x squared dx into e to the power minus infinity plus infinity e to the power minus y squared. So it is integrated, this function e to the power minus x squared minus y squared has been integrated over the entire plane. I will forget this question of x square plus y square equal to r square. So this was a question of telling you that when you have done integrals like dx dy, when trying to find, what you do is you take a strip and then integrate over the circle. So that was that dx dy is where you get the area, whereas you could have done it, you could have done this, you could have found this area by looking at circular strips over here and then integrating out. What I'm trying to do is that telling you that if I know how to do it with dx dy, how do I know how to do with circular strips? It's trivial over here because you know that this circular strip, this area is 2 pi, it is 2 pi r times dr, right? But I'm going to get that result by doing a completely different trick, doing this integral, and then I can generalize that result for an arbitrary number of spatial of dimensions. Because my whole is to find the surface area of a d-dimensional sphere. So I want, this way I won't be able to get the surface area of the, but I want to show you the trick which works in 2D, and therefore, I mean, you can, right? So, right, it is Ex squared minus Ey. So I want to write this in as as an integral e to the power minus r square, and then it would have to be something times, it is like that. It is, there is this dr, and then it is something times this dr. That something I know over here is 2 pi r. Yeah? But suppose I don't know. Suppose I don't. What I know is that dimensionally that this is an area and therefore there can be only r. Alright? So there can only be r, but no more than that. And there has to be some prefactor c, which I don't know. But then if I do this integral, the answer is c over 2, and then it is dr squared. This is going from 0 to infinity, and this is equal to the answer for the rest of it is e to the power minus r squared dr squared. So e to the power minus dx 0 to 1, which is 1. So the answer is going to be c over 2. But I know what the answer is. The answer is pi. Therefore, this c is equal to 2 pi, and the answer is that the area of that strip is 2 pi r dr. Is it?
Yes.
Huh.
R square also x square plus y square. We can figure.
Huh. So now imagine that I have d dimensions. So now imagine that you are in a you have d dimensions, and I want to do this integral. So what will happen? Minus infinity to plus infinity, minus infinity to plus infinity. There will be b such terms, and here will be x squared e to the power, let's say x1 squared e to the power x2 squared, all the way up to e to the power minus xt squared. Each one of them is a pi square root, and therefore the answer is pi to the power. Now you want to say acha. Then how do I, if it's a d-dimensional space and x1 squared plus x2 squared plus xt squared, that is equal to now my r squared. And what will be the, you will be integrating over some r. What r? Now it is a d-dimensional space, so dimensionally it has to be r to the power d minus 1 dr, and then there has to be a constant c over here. Huh? So it is c integral 0 to infinity e to the power minus r square r to the power d minus 1 dr. But this is the gamma function, right? So gamma function x to the power 2n minus 1 e to the power minus x square 0 to infinity 2 times this is equal to gamma of n. Right? So that's the definition of the gamma function. That 2 times, let's make sure that it works. So if n is equal to 1, there has to be a pi somewhere. I have to, if n is equal to 1, then this is x into the power, and then there's a dx over here. I got it right. N is equal to 1. This is x, and then for 2x dx is dx squared, and so it is 1. Gamma 1 is 1. If it is 2, then it is x to the power. If n is equal to 2, it is x cubed. The integral is x cubed dx e to the power minus x squared. So it is x cubed e to the power minus x squared, and you can write this as half, and then a 2 over here. So it is x squared d of x squared, so it is x squared e to the power minus x squared b of x squared. That's the integral, and so it is 2 times this is equal to 2 times this is 1, 2 times this is 1, so the answer is 1, and it is what we were looking at, n equal to 2, gamma 2 is equal to 1. So and now you can go to gamma 3 and check that it works and so on. So this is the definition of gamma n, so that's that. So 2 times 0 to infinity x to the power 2n minus 1 e to the power minus x squared dx, that defines the gamma function gamma of n. So what I'm looking at over here is e to the power minus r squared r to the power d minus 1 dr. So you compare with that, 2n minus 1 is equal to d minus 1. So this is equal to c times gamma of d by 2. Divided by half, maybe. So this is equal to pi to the power d over 2. So to compare with d over 2, and therefore c is equal to 2 times pi to the power d by 2 divided. So that's the connection. So if I want the in a d-dimensional space, if you want so the surface area of a sphere in a d-dimensional space is equal to, so that is c to the power c, it is a sphere of radius r is 2 pi to the power d by 2 gamma d by 2 r to the power 1. So check d equal to 1, d equal to 1 is gamma half, yes, and the answer is 2. And then you do d equal to 2, so then you have d, this is 2 pi gamma 1, then d equal to 3, it is gamma pi to the power 3 halves, and this is here, which is half square, so it is 4 pi r square. D equal to 4, it is pi square here, and this the answer is 2 pi square times r cube. So that's how it goes. And that, so this is once and for all. This is a formula which you would find that you would need it. I mean, certainly, if you are going into theoretical physics, it would be something that you would need almost every day. So the area of a surface area of a d-dimensional sphere is this. The volume is obtained by integrating out, and so that's that. So here we are. So that's the surface area of the d-dimensional sphere. So the surface area of the three-dimensional sphere, the S is equal to S times R. So back to our free particles. So free particles N free particles live in this d-dimensional three N free particles in D. So P1 squared plus P2 squared up to Pn squared is equal to 2m times C. Each one of these has three terms, px1 squared plus px2 squared and so on. So the particles live, the phase space is v to the power n, the volume of phase space is v to the power n because they are free to occupy the entire physical volume v uninterrupted by any other unimpeded by any other particle. So each one of them has volume v available. So it is v to the power n, and then it comes to they are confined to the surface of this sphere over here. So you need the surface area of this 3n dimensional sphere. So the surface area is going to be given by 2 pi to the power, so 3n by 2 gamma 3n by 2, and it is 2 mE, and then it is 3n by 2. Yeah, it's 3n minus 1 divided by 2. So that's the volume available. So this is the phase space volume So all this is, I mean, just general dynamics. Now comes the question of statistical mechanics. So you define what is known as microcanonical ensemble. That is, ensemble is the collection of n particles, and a microcanonical ensemble simply means that n particles are confined in a volume V with given an E is fixed, V is fixed, N is fixed, and the particles are free to around. So these n particles, huh?
Statement. Microcanonical.
So what this microcanonical ensemble means that I have n particles, I have fixed the total energy, I have fixed the volume, and inside this box of volume V, n particles, they can be interacting or non-interacting, they move around with energy, total energy.
Energy is fixed.
Energy is fixed.
And the volume also fixed.
Volume is fixed.
Number.
Number of particles is fixed. Everything is fixed. So now question is, how do I, so what is the statement over here? The statement then is all microstates are, the microstate is that you give the position vector of each particle and the momentum vector of each particle. That is the microscopic state. You give the x and p of each particle. So then you have the microscopic state associated with these n particles. Yeah. So n particles, it's each state is a point in this 6n dimensional space, and the dynamics is that on the surface of the sphere in this 6n dimensional space, all the points are being traversed. Get the picture that what is the dynamics? The dynamics is that I have fixed the E. And you imagine this in your mind, a space with 6n axes sticking out. For every particle, there are 6 axes: x, y, z, px, py, pz. And therefore, for n particles, there are 6n axes. In this 6n dimensional space, there exists the constraint that the total volume is fixed and the total energy, there is the energy surface, which is this, the energy surface is P1 square plus up to Pn square is equal to 2mE. So that is the energy surface, and then there is a physical volume. Physical volumes, it is V, which is the physical volume, which is the accessible volume for each particle, and therefore there is a total volume V to the power n. So you have this 3n axis, which correspond to, of the 3n 6n axis that I have, 3n corresponds to the physical, and there it is volume which is v to the power n, and over here it is a volume which is, I mean, it's a quote unquote volume, in the accessible region is the surface area of this field. If you want to make it a volume, then the point would be that you have to give a little spread in the energy. That instead of saying that the energy is totally, you say the energy lies between E plus delta E, and then the volume of the phase space is the surface area times this bit of the width. Huh? And in the n tending to infinity third and limit, it hardly makes a difference whether I'm talking about this small extension or not. And all microstates. So microstates are each point of these, all microstates are equally so that's the Boltzmann hypothesis that which defines the so-called microcanonical ensemble, that I have this microcanonical. There is no ensemble really as such over here. Generally, ensemble means a collection of systems and so on. That's not the issue over here. Issue is that I have a single n-particle system. Its total energy is conserved. It is physically constrained to lie in a volume V, and so everything is well defined. But there are a large number of microstates which are consistent with this given macrostate, and the assumption is that all these microstates are equally probable. So you just find the number of microstates, and that's the
microstates with the point in phase space.
Point in phase space. Yeah. So microstates are the points in phase space, and there is no difference between one point and the system treats all points equally.
Where constant, the particles should be point particles.
The particles are point particles. Particles are point. So that's all. So all microstates are equal. Now, fine. And that tells me that you want to get the probability of each microstate, count the number of particles, and the probability is 1 over the number of particles.
So one more thing.
Yes.
It means we are also assuming. It means we are also assuming that the known two particles can have the same microstate at any instant of time. At any particular limit of time, no particle.
Yeah, sure. Absolutely. But all this remains, you need to make one, after all, you wanted, all this was set up because you wanted to get at, formally arrive at the properties of what was then the gases. Gases had to be understood, and there was the Maxwell distribution which was going very well. And the whole point is that what is this? I mean, what lies behind the Maxwell distribution? So, what does the dynamics? I mean, if I look at after all, when you calculate the pressure, remember when we got the pressure by doing with the speed v equal to 2/3 e, that relation came by actually looking at the dynamics of the particles. Huh? So the dynamics of the particle were responsible for this pressure. We made some assumptions about the collisions and the imparting of momentum and arrived at this answer over here. So question the Boltzmann picture that I have this large number of particles, and let's say I want to arrive at that P equal to 2/3 c, then what is the mechanism of getting there? So I have got one step there. I have taken a step saying that my picture of these n particles moving around is that I look at the dynamics which is given by x and p. By that time, everything about Lagrangians and Hamiltonians were known. So therefore, the particle dynamics is given by p and small q and small p. And I have these microscopic, all of them absolute. But all right, that gives me a way to count the number of microstates. But what thermodynamic, after all, pressure is a thermodynamic quantity. What thermodynamic quantity do I calculate gamma EVN, the accessible volume in phase space? So the accessible volume in phase space is this. And what does it have to do with anything which is of the thermodynamic? And therefore comes the next big statement that the entropy is what is connected, and S is equal to A. So microcanonical entropy is found from S equal to. So all microstates equally probable, and the next step is this, and that in the Stackman, as we will, is basically based on these two statements over here. One is that all microstates are equally probable, and second, that the number of microstates gives you the entropy to this equation. So therein lies that's the foundation, the entire foundation. I mean, now it's a question of, all right, I mean, how plausible can you make these statements and so on and so forth. But so far, that's a whole area which people work for, a lot of people are interested in and trying to understand it better and better. But the basic statement are these two, that all microstates are equally probable, that is, all microstates consistent with a total energy E, a total volume V, and a total number of N particles. All these microstates are here, and they relate to thermodynamics through this relation. Now,
did he calculated this logical step to add this part, but just
yeah, because see, the Y is somewhat only you assume that there must have been a lot of back and forth in his mind about. But once you have got, see, we have the gamma, which I mean certainly he could have. He was aware of. You say it is S. Now you need But now thermodynamics is going to tell you the rest, because you know that the temperature, which is missing in all this, is obtained through del S del E equal to 1 over T at constant NLP. See, so it is very likely that things were arrived at. I mean, this connection comes back calculation, that in the sense that I know gamma from over here, and I ask myself the question that eventually I would need I would need to describe the temperature. I have to go to Pb equal to nkt. Yeah, I mean that is ideal gas. I mean that Pb equal to 2/3 C is the same as Pb equal to nkt, and therefore I need the temperature. And the temperature in thermodynamics is related to the entropy by this. And entropy is vague in thermodynamics. So here is particle dynamics giving me this quantity over here. This, you see, entropy is extensive. Therefore, you must take a look. Over here, things are raised to the power n. Extensive is requires that, I mean, it is proportional to n. So there has to be a log. And therefore it is, I mean,
That was one of the logic.
very large. But I mean, if I have to justify it to you, I mean, that given this over here, I mean, entropy being extensive, the first step that you would have to take.
One of things, temperature, which we are considering, is a sort of great quantity thermodynamics, because we don't have any specific description. It is coming from the entropy. But does it have a microscopical description? From where it arises?
What?
Temperature. There must be some.
I mean, that was, see the Maxwell picture of it's the fact that the specific heat was related. I mean, it is the measure. I mean, the energy was the measure of the energy which these gas molecules and energy came. The specific heat came from the energy, which in turn which energy was all kinetic energy, and therefore the point is that your temperature would somewhere along the line would have to be related to the energy. Yeah? So because its specific heat is delta del T. So the energy would have to be coming from the temperature rather. The temperature would have to be coming from the kinetic energy that these particles have. And I mean, the thermodynamics was, I mean, once you take this, it gives you a totally consistent phenomenology of energy, specific heat and things like that. So this is actually, I mean, you go with TDS. So you do this, and then, I mean, because this was dq over here, the dt is actually the specific heat. Yeah. So, I mean, you can see the point that if I have the volume fixed over here, this is TDS, this is related to the specific heat, and therefore this is related to the energy must be coming from the molecular motion. Right?
So energy part is quite It's
Uh,
clear because kinetic energy is half this way.
Yes, right.
Defined in that.
So if energy comes from the molecular motion, then this tells me I had better relate the entropy to the molecular motion.
Yeah. And one more thing is, temperature is quite familiar because you can measure and feel temperature.
Yeah.
But still, somewhere or other, it has to be appearing at some of the microscopic levels, which in turn gives a different temperature we feel in our daily life or thermodynamic skills. But what are the microscopic description of temperature? From where it is?
See, it has come from the energy only. See, the point is that energy is determined, the entropy is coming from the, is being directly related to the energy, which is the kinetic energy of the system. I mean, all this came because E was equal to P1 square up to Pn square divided by 2n. No? So you are making a direct connection with the energy and the
is it some direct connection between energy or temperature, or is it some kind of energy transformation that is taking place between the mechanical energy that we are talking about, half mv square or like that, and there is some kind of energy transformation going on from that type of energy to other type of energy, which in turn gives us T.
No, but you are really not transferring energy right now. All that you have is an isolated system with n particles. So there is no transfer of energy going on, except that, I mean, these molecules, see, as the molecules, there are forces, all these collisions are also elastic collisions, which one.
Yes, sir. So then in certain system, suppose the system is infinitely big, suppose the molecules or the atom, the particles which are there inside the volume can't collide with each other, neither they can collide with each other, nor they can collide with the walls of the content because the content is infinitely big. And in that case, they are not able to transfer their energy neither to the wall nor to other particles. So, will we can describe a sort of temperature like that in that system? Because when the energy is not getting transferred.
Oh, but yes, sure. I mean, the moment, I mean, thermodynamics tells you that E is equal to 3n kT by 2, you are saying that so long as there is no, I mean, energy can only be transferred if I put two bodies with different temperatures in contact.
This temperature is coming only because they are somehow interacting.
Yeah.
So if I switch off all the interactions and let them move freely among themselves, neither they can collide with the walls of the container. Because I am making this hypothetical situation. Suppose the container is too big to collide with the container. In that case, I think, means I don't know whether we will be able to detect temperature in the system.
No, the point is that the temperature again is a isolate. I mean, unless you do something to this system, the relation. I have that I have to put it in contact with a system at a different temperature. No, I mean that can only allow the, which essentially is all right. I mean molecules of one kind colliding with different kind, and therefore, I mean, there can be yeah. I mean, yes, right. I mean, the whole business of, I mean, when you take two systems and put them in contact in the molecular motions, then you would have, I mean, which is precisely what the, I mean, Boltzmann transport does, that you look at these collisions between the particles, and then you have to, I mean, sort of see that if I have a difference in temperature or pressure and so on, they would eventually have to come to equilibrium at in some form or other, which is, yeah, I mean, interactions are essential. I mean, I have to switch on non-interacting particles. I can't, if this is the only form of energy, I can't do anything with it. I have an isolated system and it's not going to do it. I have to have an interaction in order to, I mean, all right, so here we are. We have got entropy, we have got this, and then so that. All right. The next step in this game is that I have this gamma, which is written over here. Now I have to take take the log, and actually, so maybe I'll just take the log and leave it at that for today. It's a pretty, we have come a pretty long way, and we'll pick up from there next time. So I'll take a log. S over k is n log b, because this part is does require plus what's this?
What is surface area 2 by to be by dy?
This 3n by this. Why is this?
So this is the term for the C actually.
The 2 is coming because of the series. If you have constant 2 initially, the 2 would not have been coming back here.
So to make the gamma function.
While calculating the surface
Oh,
area.
Ajay, this came from the from the surface area of the. So this. It's 2 without. So 3n log pi. Really, that's not. Here is where the issues are. 3n by 2 log of 3n by 2. I'll drop the half in comparison to that. So it is 2me, and that's these dimensions of 2. There was an h which I have dropped. So somewhere, what was I calculating? This is d3p, d3, it has to be the number of states. It should have been d3p, d3r, and there should have been divided by h to the power, right? I mean, n. So this is dimensionally a bit off. This has to be a dimensionless number. So there is it's a number of states. So ME is like P squared. So ME is P squared. So this is P to the power 3n. This is X to the power 3n. So in principle, I should have, have the number of states would have a H to the power 3n.
Yeah.